Hello again. Welcome to video lecture number 4, which covers section 0.3, Algebra 1 Review, Number Sets. Please take a moment, as always, to read through the objectives associated with this lesson. By the end of this video lecture, I hope you're able to classify and categorize various numbers into their number sets or families of numbers. The first page, as you can see, is nothing more than several definitions, because in order for us to categorize certain numbers into categories, we need to be able to know what those categories are. So we will start by defining each category one by one and providing some examples of what numbers fit that category, and then some examples of numbers that do not fit that category. As opposed to starting at the top like we normally do, I'd like us actually to start down at the bottom of this page with natural numbers, and we will work our way up. This way I think you can get a little better understanding of how these number systems are or have relationships to one another. We begin then with the natural numbers. Natural numbers are defined to be any number that exists in the following infinite set. So notice the infinite set there, and hopefully the ... is pretty self-explanatory. It means the pattern continues. So although I didn't list 5, 6, 7, 8, and so on and so forth, those numbers are definitely part of this set. So if you look on the left, you see numbers in green. Green meaning go. Those are correct examples of numbers that would fit in this set. On the right, you see numbers in red. Red means stop. Those are numbers that are not natural numbers. So for example, if you take a look at -6 over -2, although it may not look like one of the numbers in the black set, it can be when you simplify it. -6 over -2 is +3, and definitely 3 exists in this set. So once again, all of the numbers in green fit that category, and all the ones in red do not fit that category. Obviously, I've just provided you with some examples, not all of them. And you need to know that this is the most basic of all number sets, with 1, 2, 3, 4. We call these the counting numbers, the numbers that you start in grade school with. So next, we'll move on to whole numbers. Whole numbers are defined to be any number in the following infinite set. And you might be saying, well, this looks identical to the last example, but there is one small difference. That would be the number 0. So basically, wholes can be thought of as the natural numbers plus 0. That's the only difference. So if you look in the green, the examples are given there, and in the red, those are some examples of numbers that are not whole numbers. So some themes here between the first two sets of numbers. There are definitely no decimals in either whole or natural numbers. So that's one common thing you want to be aware of. Another thing the whole and natural numbers have in common is that neither of them have any negative numbers in their sets. So if you want to compare those two, they are pretty similar. Moving on, we will now define integers. Integers are probably the most widely used number set in all of high school mathematics, and they're defined to be any number in the following infinite set. Do you notice what's different about this set compared to the others? Well, it's definitely the fact that integers include negatives as well. So if we want to build a definition for integers based on the previous ones I gave you, we could say that integers are the whole number value set plus negative numbers. And I would say negative non-decimals, because there is a similarity between the first three definitions I've given you, and none of these first three number sets use any decimals. So once again, if you look in green, you see some examples of numbers that are integers. Now, 8 over 4, although it looks as a fraction, simplifies to positive 2, and since that's not a decimal, it does fit in the integer category. If you look in the red, those values obviously include decimals, so they are not integers. The next set of numbers on our list are the rational numbers. They're defined to be any number that can be, emphasis on can be, written as a fraction in the form p over q, where both p and q are integers. Now, I've shown you some examples here, and yes, we're going away from the set definition. It makes more sense to define rational numbers with words than it does a set of numbers like the previous three. So if you look at -7, notice the key word was, or key phrase from the definition, can be. -7 is not written as a fraction, but it can be. If I look, both -7 and 1 are integers, so that is a rational number. 0.3 repeating, while not written as a fraction, can be written as 1/3. Since 1 and 3 are integers, that makes a fraction. That makes 0.3 a rational number. Another example, 0.123 can be written as 123 over 1,000. Since that decimal comes to an end and stops, you can kind of get the idea that it will be written, or will be able to be written, as a fraction. Now, if you look at the note I made here, if you take a look at 2.75468, and then I put 3 dots, meaning the pattern could continue. If the decimal doesn't come to an end, meaning it's non-terminating, and there's no pattern to the decimals, notice 7, 5, 4, 6, 8 are pretty random, then you can assume that it's not a rational number. Now, I will say that all of the numbers below rational on this chart so far are all considered to be rational numbers. So that's how those 3 previous number sets are related to rationals. Next, we have the irrational numbers, and simply put, they are the exact opposite as the rational numbers. As you can see in the definition, it states these are any numbers that can't be written as fractions using 2 integers. So for example, a lot of people will look at pi and say, well, I can make pi a fraction by putting it pi over 1. Well, if you do that, pi, remember, is not an integer. It is a decimal itself, so this would, of course, violate that principle that they both have to be numerator and denominator integer values for it to be considered a rational. So all of the numbers in green are what we would call irrational, meaning there's no way we could write those as fractions. The second to last number system on our list here are the real numbers. And using definitions we have previously just written down, we will define real numbers to be all rational numbers plus all irrational numbers. And if you look closely, you may be seeing this pattern that all of the numbers that fall below real numbers on this list are all considered real numbers. So if you look in green, I have a few examples there, and in red, I have some examples of what wouldn't be a real number. Simply put, the only type of number that is not a real number is when you take the square root of a negative number. For example, square root of -2, square root of -4.7, or even the square root of a -100. Finally, we have the complex number system, and we will spend a great deal of time talking about them in Unit 1 with quadratic functions. However, for now, let's just take the definition as any number in the form a plus bi, where I is the square root of -1 and a and b are real numbers. Simply put, for now, recognize that any single number you have ever seen in your lifetime is a complex number. There are no non-examples to speak of because, again, every number can be thought of as a complex number. So don't think of complex being difficult. You know, sometimes we say that word complex and we mean difficult or hard. That's not what it means here. Again, simply put, just remember that all numbers that fall below complex numbers all can be classified as complex numbers as well. Now that we have the definitions for all of the number sets, it's time to start thinking about the relationships to one another. So I have a classification chart that I'd like you to copy down, and after you copy it down, let's take a second to read over it and understand how it works, because I really think this will make your lives easier. So I've written a note here in red that says if a number belongs to any one of these sets on the chart, it must also belong to all of the sets that are listed above it. For example, if we consider the integer -2, when I look on the chart, I notice that integer is positioned below rational, real, and complex, and notice the left side is not connected to the irrational side, and that kind of shows you that irrational is off on its own and doesn't have as many similarities to the other number sets. So -2 is an integer, but it's also rational, real, and complex. If I took a natural number, say 3, well, since natural is at the bottom of this chart, 3 must also be considered then as a whole number, an integer, a rational, a real number, and a complex. I've also provided you with another visual, a Venn diagram, that may help you understand the relationship between the number sets. So now you have 2 diagrams, and use whichever one works better for you, but let's talk a little bit about how to read this Venn diagram. So for instance, if I pick a number, let's say an integer -2, and I place it in the integer bubble, notice that the integer bubble is completely within the rational bubble. So that must mean that -2, while an integer, is also a rational number. Since all of the bubbles on the right are contained within the larger bubble of real numbers, that must mean -2 is also real. And since the entire bubble is housed within a rectangle that says complex, -2 must also be a complex number. Notice what -2 is not. -2 is not irrational because it is not contained within those bubbles. So now we move on to our first example after several definitions and thinking about the ideas between them, which says name all sets of numbers to which each number belongs. So in no particular order, I'll start with letter D. If you take a look at letter D, I notice it's the square root of 7. With these numbers, it's better to get their decimal interpretations before you actually start classifying them. So with square root of 7, if you look on your calculator, it will read 2.645751, and then the digits go on. I look at those, and since there's no pattern to these decimals, right, no pattern at all, and the decimals don't stop, there must be a first classification of an irrational number. Now, since it's irrational, if I go back to my number chart, I'll notice that irrational numbers are positioned beneath real and complex numbers on those charts. So because this number is irrational, it's also real and complex. Example 1b is -18. Well, there's nothing we can do to simplify it, so I notice that it's a negative value. So the number set that starts giving negative values is integers. Well, if I look at my number chart above integers, I notice that all integers are also rational numbers. So -18 is also rational. It can be made into a fraction. It's real because all rational numbers are real, and it's complex because all real numbers are complex. So you actually have 4 answers. And by the way, for all of these, you should be using complex, because as we discussed, every number is technically a complex number. So please try the remaining exercises from example 1 that I did not cover, and you can check those tomorrow. Example 2 states, give an example of one number not already used in the notes that would satisfy the given conditions if possible. So I will start with B, and B asks us to come up with any number at all that is both rational and irrational. Well, simply put, that's not possible. All numbers are either one or the other, and if you look on your number charts, notice that the irrational and rational sections are completely separated from one another. Next, we'll try letter C. It asks, find a number that is real, rational, and an integer. Well, I would ask myself, which one of these number sets is towards the bottom of that first number classification chart I gave you? Well, the integers are on the bottom, so let's start with coming up with an integer. Well, an integer, for example, I could use as -4. Since -4 is an integer, and it obviously falls below the other two number sets on the diagrams, then it must also be rational and real. Remember, -4 can be written as -4/1, which makes it rational. So here is one example of an infinite number you could provide here that satisfy example 2C. Well, this concludes video lecture number 4. Please complete example 2A and 2D, and on the space provided below or on the back page, write at least one question you have after watching this video. Okay, good luck, and we will see you tomorrow.